So we'll start this review by defining work. And so to think about that, what we're going to do is we're going to think about a ball. And so if we hold a ball, the initial velocity is 0, and release it, it's going to fall. And as it falls, it's going to gain speed. And so the reason that it's gaining speed is because there's something pulling it, and that, of course, is the force of gravity. So we have Fg, pulling this down. We know that from dynamics. Now, for energy and work, what we first have to do is we have to define a system. And so in this case, the system is probably the ball, right? So we'll say, I'll just put this dotted line. So this is our system. It defines the system. And so work is going to be a force, an external force, something outside the system, out here in the environment, which is acting on the system to put energy into it or to take it out. So in this case, the force of gravity is actually putting energy into this, and we'll define energy in a later section. But it's putting energy in, and we can see that energy. It's getting faster and faster, so it's becoming more energetic. And so we can define work to be the transfer of energy into a system, or if I reverse this and I threw it up, then the ball would slow down, so it would lose energy, or it's the energy flow out. And that's what we're going to define as work. So if we put energy in, then we call that positive work. And if we take energy out, then that's called negative work. And so this is what we'll be analyzing. We'll be thinking about how forces, external forces, act on a system and how we can calculate that. And then later we'll come back and do it from an energy-wise. So in general, what we have is that the work done on an object or on a system is going to be the force times the displacement. It's actually dotted with the displacement. These are vectors, and so it's actually going to end up being the force parallel to the displacement. So let's see. Let's do a simple example. So suppose that I have a solid surface, and I have a box sitting on the solid surface. And then on this box, what we're going to do is we're just going to apply a force. Maybe we tie a rope to it and we're going to pull it across the floor. So we have some force, let's say 3 newtons. And then we're going to pull it a certain distance. So let's say, 2 meters. Delta x is 2 meters. Okay, so now we can calculate the work done. So the work in this case is going to be the parallel force, we'll talk about what that means in just a minute, times the displacement. So the work in this case, the force is parallel to the displacement. It's in the same direction, or it's in the same coordinate, so it's like one-dimensional. We have x and y. So since the box is moving in the x direction, we want the force in the x direction, and that's all of this. All of this force is in the x direction. And so we can just substitute in, and this is going to be the magnitude would be 3 times the displacement. Let me put some units on that. So that's 3 newtons times 2 meters. So we get 6 Newton meters. And this right here, the Newton meter, that has a special name. That's what we call a joule. So it's 6 joules. And that's the same units we have for energy, which when we get to, you'll see. So the work in this case of pulling it with 3 newtons over 2 meters is going to be 6 joules of work was done. So that's how much energy was put into the system. Now, what if it was not parallel? So what if we didn't have this? What if there was some angle? So let's do an example like that, and then we can generalize our definition. So same box, but now what we're going to do is we're going to connect the rope at an angle. So we pull with a force, and again I'm going to do 3 newtons. And we're going to have the same displacement, 2 meters. So do you think the work will be less than, equal to, the same? So let's think. Okay. So let's analyze it, and then we can answer that question. So again, I want work is going to be the piece of the force that's parallel times the displacement. But in this case, the force is not parallel. And so what I need is I need the component which is in the same coordinate direction as the displacement. That's what we need to find. So we need to find this fx, because I'm calling this the x direction. And so I'd have some angle theta. Oh, I forgot to say an angle. Let's say 10 degrees. So based on our previous work with trig, we can find that. So fx in terms of f. So since it's next to the angle, that's going to be cosine. So it's going to be f cosine theta. So fx is going to be f cosine theta. So now I'm going to substitute that in here. So we get work is going to be the force in the x direction times the displacement in the x direction. And then we just said, well, fx is going to be the force times cosine theta times the displacement. And if I just kick this over, then I get work is going to be force, the magnitude of the force, times the magnitude of the displacement times cosine theta. Where theta, this theta, that's the angle between the force and the displacement. So force and displacement. That's theta. And this is our more general form. So now we can alter our definition up here. So it's the parallel force, or we could just write it as the magnitude of the force times the magnitude of the displacement times cosine theta. And this works for any of them. So like in this case, this the angle between the force and the displacement is 0. So we would get cosine 0, which is 1. So that way it's just the force times the distance. So that works out nice. All right, let's calculate. So the work is going to be 3 newtons times 2 meters times cosine 10 degrees. And if we calculate that, I think it comes out to about 5.9. I'm not going to plug it in, but so we get about 5.9 joules. So we can see that it does a little bit less work. Actually, let me calculate that, because I know somebody's going to check my arithmetic and I didn't really calculate it. You have to give me 1 second. So 3 times 2 times cosine 10. Yeah, 5.9. Okay, so I'm good. So we lost some work. Well, it kind of makes sense. As the angle's increasing, what's happening is as the x component is getting smaller and smaller and smaller, so we have less force that's actually pushing it in the direction of the displacement. So our overall work should decrease. And that's the case. And if we think about it, it's just this cosine theta that's changing it. So I know most of you have not studied in pre-cal. You haven't looked at the cosine function. But the cosine function, when the angle is 0, we get a value of 1. And then when it goes to 90 degrees, it drops all the way to 0. So this would be like at 90 degrees. So that's an important thing. If it's perpendicular, it's not going to do anything. And then if we go all the way over, if we have an opposing force, if it's this way and the object's displaced this way, then the angle is 180 and it dips all the way back to -1. So we get this kind of graph. Anyway, it's terrible, but that's 180. I'll show you what this one means. Okay, so basically as you move the force in this direction, what you're doing is you're reducing the amount of work that's done to move it. Okay, let's look at this 180 thing since I talked about it. Sorry, stray marks. So let me do one other example. So say an object is moving. it already has velocity, and it's moving this direction. So it's going to be displaced 2 meters. But now what we're going to do is we're going to pull backwards on it. So we're going to be, we have some force. It could be friction or whatever. It's just a force. We'll say 4 newtons of force over this 2 meters. So you can see that the force is opposite of the displacement. So now we can use our work definition. So that's going to be the force times the displacement times cosine theta. Magnitude. So the magnitude of the force is 4 newtons times the displacement, 2 meters, times cosine 180. Because that's 180 degrees. Our displacement vector, if I move it up, is right here. So we see that the angle is 180. So what I get is I get 8 joules, but cosine 180 is -1. So it's -8 joules. So I can see that when the force is opposite the displacement, I get a negative. But when it's in the same general direction, then we get a positive. And that's true in general. So let's generalize this. So we have, number one, our definition. Work is going to be the force, the magnitude of the force times the displacement times cosine theta. And then if the force and displacement are in the same direction, then that's positive work. Whereas if the force and displacement are in opposite directions, then it's negative work. And then there's a couple other things. Well, here, let's see. So say I have a displacement vector like this. That's our displacement. So if the force is like this, since it's pointed in the same general direction, that's going to be positive work. So it doesn't have to be exactly in the same. And as we increase the angle, so when I go from theta 1 to theta 2, I'm going to have less x component. So as the angle increases, it decreases until it's perpendicular. And at 90 degree force, or perpendicular force, a force which is perpendicular does no work. No work. And so I think that's it in general. That's the the definition, and then some other things. So why don't we work through, I'll do a couple examples for you of things to think about when you're going to calculate work and why it comes out the way it does. So let's take this. Suppose we have this guy holding a box. So he's just standing there holding a box, but he has to hold the box for 14 hours. And so he stands there holding the box for 14 hours. How much work did he do? So to think about that, we can look at the definition. So let's see, it's going to be force times the displacement times cosine theta, the angle and stuff. Okay, so let's think about the force. So is he applying a force on it? Well, sure he is. He's holding it, so he would be holding it up in this direction. So that would be like the force of his hand, right? And so we know there's a force. So whatever that is, that would be equal to mg in this case. So we would get mg times the displacement. So now the question is, how much did it move? Well, we said he was standing there for 14 hours holding it still. So the displacement is 0. And so then I don't even care about the cosine because the work in this case is 0. So if there's no displacement, then there's no work. If it doesn't move, there's no work. All right, let's think of another one. So what if he walks with the box? And this one's it's tricky. It's always presented a certain way, but in fact, I'll talk about it. So let's suppose he's standing there again. He's holding the box, but now he walks, and he walks some distance. Is there work done? So we have to think about work is force times displacement times the cosine theta. Throw that in there. So now we have to identify the force again, and we're going to have the same force. So the force is this, the force of the hand, and the displacement is this. So it seems like, okay, well, we have displacement, so there's got to be work. But there's not. Because the work would be the force of his hand times the displacement times cosine 90. And as I said earlier, cosine 90 is 0. So we get 0 times all of this is 0 joules of work. I need joules on that. Now, this is in general. It's how it's generally presented. But there's actually, if he was actually doing this, there's a little bit of friction here that's pushing it. Static friction that's holding it on his hand. Otherwise, when he walked, this thing, the box would slide off of his hand. But we're not going to overanalyze it. That's just in general. So the trick, or not trick, but the thing to keep in mind is that when you're analyzing work, you're going to have to go back and figure out all the forces. So this just comes out of our study of dynamics. You know, was there friction? What are any external forces acting on our object of interest? And then we can analyze those. So the last thing I wanted to comment on was what happens when there's multiple forces acting on an object, multiple external forces. So let's go back and let's do the box. This time we're going to add friction in though. So we have a box, and what we're going to do is we're going to apply a force. I don't know, I guess I'll do it at an angle. So we're dragging it with a rope. So we have the force of the rope, or tension. But this thing has friction. And so we're going to have a force of kinetic friction. I'm just going to draw it up here, just so you can see it. So there's our kinetic friction. So the question is, what is the work being done? So what's the total work being done? And so the work, what we can do is we can think about this. So, the displacement is this way. So that's our delta x. So we know that this force is doing positive work on it, but this force is doing negative work on it. So what we can do is we can think about them separately, and then we can maybe put them together. So the work of the rope would be the force of the rope times the displacement times whatever, cosine theta, right? Times cosine theta. Okay. And then the work of friction, it's opposite in direction, so that's going to be negative force of kinetic friction times the displacement. It's negative because that's cosine 180, or that it's doing negative work, whichever way you want to think about it. So the total work, or the net work, would be this plus this. So we get the force of R delta x cosine theta minus the kinetic friction force times delta x. And if you notice, we have a delta x in both of these. So what we're going to do is we're going to factor that out, which leaves us with FR cosine theta minus the kinetic friction times delta x. And if we think about this term right here, well, that's the force in the x direction, isn't it? So the force in the x. So we get the net work on an object would be the force in the x direction minus the kinetic friction force times the displacement. And this right here, what it is it's this force plus this force. So the net work is going to be the net force in the x direction times the displacement in the x. And so we can see that what we can do is we can either deal with the work separately We can do the work of 1 plus the work of 2. That's what net work means. Or we can just deal with the force. We can just add up the forces and multiply by the displacement. Either one of these works. It just depends on how you want to analyze it. I guess there's one more thing that I wanted to mention. Sorry. And that's what happens with like 2-dimensional or 3-dimensional. So 2D or 3D forces or motion. So if I have an object, it starts here, and we apply a force and we move it over here. So I don't know, the force of 2 newtons over 5 meters. And then we move it this way with a force of 4 newtons for, 6 meters. And then we move it like this way. A force of 3 newtons for 8 meters. So when we want to deal with this kind of stuff, just like we did previously, we can deal with each segment independently. So the total net work would be the work of segment 1 plus the work of segment 2 plus the work of segment 3 and so on. So that would be this force times this distance. So we get 2 newtons times 5 meters plus the work in this direction, 4 newtons times 6 meters, plus the work of the last section, which would be 3 newtons times 8 meters. Then we just multiply and add. So we get 10 joules plus 10 joules. I'm sorry, 24. I don't know what I'm thinking. It's getting late. Can't think. 24 joules plus 24 again, right? I don't know. If I messed up the math, oh well. Anyway, and then we just add those up. 24 and 24 is 48, and 10 is 58. So we get 58 joules of total work. So we can deal with these independently. And that's good, because if we have a force acting in 2 dimensions, I don't know, we have a force and then we're displacing the thing, we can separate it into components. And then we can deal with like our x components and our y components, just like we did with projectile motion. So we can deal with these independently and then add them together and stuff. But that's it. Okay, so that's it. And then I might do a video with a couple of examples. Actually, I think that's it. So from here, you should be able to work. So the next thing will be to go through some practice problems and try to apply this.